Good morning and welcome to today's webinar on coupled high-frequency electromagnetic simulation and thermal simulation inside Solidworks. My name is Arvind Krishnan and I will be your presenter today. Let's take a look at the agenda for the day. We're going to start this presentation by briefly talking about what is HFWorks, and we're going to look into the capabilities of the software, and especially with regards to the thermal coupling between HFWorks and the thermal simulation. We're going to look at two key power handling issues that are present in passive microwave components, and we were going to look at how HFWorks deals with them. Finally, I'm going to use a demonstration, a couple of demonstration examples to highlight this capability inside HFWorks. Now let us begin by talking about HFWorks. HFWorks is a 3D field simulation software, basically for designing and studying the performance of passive RF and microwave devices. It is fully embedded inside Solidworks, and it is also a gold certified partner product of Solidworks. It's easy to use and it can be used in both desktop, laptops, etc. And it is the de facto standard high frequency simulation suite for Solidworks users. Before we begin, I just want to introduce a small promotion from our sales department. For people who are looking into this webinar, either live or through the recording that was sent to you, if you are interested in trying out HFWorks, we are offering you a 1-month free trial with complete technical support. To be eligible for it, you need to send an email to sales@hfworks.com with an appropriate subject that is specified here, and then we will facilitate the trial as soon as we receive your email. Okay. And once you complete the trial, and you will be given an option to buy HFWorks at a discounted price. For more details, please contact sales@hfworks.com. Now let us look at HFWorks capabilities briefly. HFWorks as a product can do 3 broad types of simulation. First is the antenna simulation. As the name suggests, HFWorks will be able to simulate the performance of antennas, be it printed antennas, horn antennas, etc. The next one is a generic parameter simulation that is used to study the performance of filters, couplers, etc. or any passive RF and microwave device. The HFWorks gives you the S parameters, which can then be used in further circuit simulation of your passive components. And finally, HFWorks is capable of computing the electromagnetic resonance inside any passive component, any structure. So these are broadly the 3 main study types that HFWorks permits today. Next, we look at some of the applications of HFWorks. HFWorks is mainly used in electronic component design, basically in designing passive components used in both RF and microwave field. Okay. Some of the applications are illustrated in this particular slide, and they include couplers, filters, multiplexers, etc. You can do all kinds of antennas, antenna feed networks, EMI, EMC type of problems, PCB, printed circuit antenna, printed antennas, and so on. So it's really a program that can cater to a wide variety of industries, ranging from high technology, electronics, aerospace, defense, consumer products, etc. There are 2 key issues that designers of passive microwave components deal with, especially with regards to power handling. Okay. First is, will there be a dielectric breakdown? So what does it mean is that will my electric field reach a certain level so that enables the breakdown of the dielectric? Okay. And where exactly inside my model is that particular condition being reached? Now this is basically what is known as the peak power handling or the peak power rating of any particular device. Okay. Now the peak power rating or the peak power is by design, it's only expected to occur in very short periods of time and not a general operating condition. Now let's get to the next type of issues grappling designers of these devices. That is actually the thermal aspect. How hot does my device get? And that is determined by the continuous power handling ability of that particular device. Okay, when the device is operating on a continuous mode, obviously it's operating at a much lower power than the peak power, and this leads to the heating up of the structure. And whenever there is heating, and if the temperature reached is beyond what is prescribed for the components, then it's always a problem, and it could lead to malfunction of the device, and that's something as designers we would like to avoid. Now just as a recap, how does HFWorks deal with these power handling in these high power microwave devices? Now let's start with peak power. Now HFWorks is capable of giving you the electric field plot inside your entire model, and it is also capable of plotting what is known as the factor of safety plot for the electric field, where it highlights the areas where dielectric breakdown can occur. In the case of continuous power, and this is a topic for today, HFWorks is capable of plotting the temperature within a structure. So you can pinpoint locations where the temperature exceeds a certain value. You can also use what is known as isoplots to study hot zones. And you can do different types of cooling mechanisms using what we know as heat transfer coefficient boundary condition. Next, we will be looking at a live demonstration. I'm going to take a couple of examples to highlight the coupled EM thermal simulation in HFWorks. The first one that you see on the left is a double-ridged waveguide transition from a coax cable, and we will look at how hot the components get when the device is operating at continuous power mode. And on the right side, I also have a waveguide that's basically a circular waveguide, and you will see that there is some sort of dielectric sitting there. And when I send in high power microwave, we're mainly interested in how hot does the dielectric get under the operating conditions. So we're going to look at these two examples now. What you see here is a coax to double ridge rectangular waveguide transition. This is designed using Solidworks. And now we will do a simulation using HFWorks. Notice that the model, the assembly designed in Solidworks is ready for simulation right inside Solidworks using the HFWorks manager. Now HFWorks, as I mentioned earlier, is an add-in product to Solidworks. It's a gold certified add-in product that allows you to do simulations in your passive RF and microwave devices. Now in this particular example, we're going to do a few scenarios that we outlined earlier. The first scenario is the peak power. Now we're going to see how does this structure respond to the peak power. Now during peak power, the main problem is in the electric field or the dielectric breakdown. Okay. That is done using a peak power study that I've already set up. To set up a study in HFWorks is extremely simple. You just have to right click on the topmost assembly that you see in the HFWorks manager. You create a study. There are three different types of study types. As we said earlier, there's parameters, resonance, as well as the antennas. In this particular case, it's the S parameter study that we are interested in, and you can couple that to thermal simulation. Here we are just going to start with the S parameter study at peak power of 1500 watts. Okay. Now the operating condition of this particular device is at 6.72 gigahertz, and we will be able to find that out by doing another S parameter study, where which you find out between a certain range of frequencies how this structure responds, and how basically how does the S parameter look in that range of frequency. So that I already created that. We will be able to look at a linear chart of the S parameter value in decibels versus the frequency. As you see here, the best operating frequency is about 6.72 gigahertz, and that's really the frequency in which we will be doing the worst case scenario or the peak power condition. So we'll look at the study of peak power. We define the materials inside HFWorks. Really simple to define. The waveguides are made of copper, and then the signal is injected using a coax cable, and the coax cable is another assembly of 3 components with its own materials. Then we specify the port boundary condition to specify the port. Now this is the port, and this port is excited with 15 kilowatt of power. That is really the peak power or the peak operating condition, which is really exists for a very short period of time. And then the next port is here, and that is just excited. Now we are interested in computing the electric field. I've already run the simulation at 6.72 gigahertz, and we will take a look at the electric field. Now we can take a look at the section plot of the electric field. From this particular section really tells you what happens, right? Now when you take a look at this electric field, you notice straight away that these red areas, the hot spots, which is really close to about let me expand this, and this red is really close to about 3.1 e to the 6 volt per meter, and for air the dielectric breakdown is 3 e to the 6 volt per meter, and you know straight away that some kind of breakdown is going to occur when this particular structure is excited at peak power. So and you know that this is something you want to avoid. So when you rate this particular device, you would like to tell that it can only operate at a peak power which is less than 15 kilowatts. Now you can also plot an electric field as a vector that kind of shows you what really happens, and also an isoplot that tells you the region in which there is chance of a breakdown occurring. So so basically right around the coax cable there's a possibility of breakdown. Next we will look at the average power operating condition. The average power is, unlike the peak power, is just set to operate at 800 watts. We do a similar study, but when we define port 1, we excite it with 800 watts of power. And then we apply a convection boundary condition to all the outer faces of this copper. Okay. And when we run a simulation, we will be able to compute what is the temperature. Okay. Now here is a section plot of the temperature in the structure. So basically you can see that the coax cable getting heated up all the way to about 218 degrees C. And it's important and imperative that the material that the coax is made of can withstand this type of temperature. And because this is the operating condition with average power, you know, this is a condition that exists for a very, very long period of time. And then engineers can make decisions about what materials to use and so on. So this is very useful because it can give you an idea of how the temperature is distributed inside your model, inside your structure. You can define the temperature as a 2D plot here. Really, we have taken a couple of points and we have defined how the temperature varies between those 2 points. It's basically between a couple of points in the model, just taken 2 points just to indicate how temperature can be expressed as a 2D plot as well. And finally, you can isolate components. Let's say we are only interested in the waveguide and we would like to understand what happens to the temperature. Here it is, and how hot does my copper in my waveguide get. We noticed earlier that the coax reaches over 200 degrees C, but whereas the copper does not get heated beyond 54 degrees C. And these kind of temperatures are very useful for engineers to see under what conditions their devices are going to operate. Next, we will take a look at a circular waveguide, as you see here, and determine what really happens to the dielectric. How hot does it get when a microwave at very high power is injected inside this waveguide. Again, the principle is the same thing. We design the components using Solidworks as an assembly, and then we activate the HFWorks manager where our studies are organized. The first thing is really to find out what is the operating frequency for this particular device, and that can be done simply by doing an S parameter study, by specifying the ports as before and taking a look at how the S parameter varies as a function of frequency. As you notice here that this graph gives you both the maximum decibel in the negative, where this is really the operating condition. This is where your device waveguide is the most efficient. It's about 9.4 gigahertz, and you also notice here you can even get a sense of the bandwidth. Okay. So we will actually do a simulation at 9.4 gigahertz, and at this particular simulation is where we couple this to a thermal simulation. So we're going to do this study at just one frequency, 9.43 gigahertz, and you're going to couple that to a thermal simulation. The materials are defined as before. The only thing to note is this dielectric block has a particular material and has a particular thermal conductivity associated with it. And there is the waveguide is made of copper, and everything else is air. The ports are specified as before. When you define a port, you set the excitation. Now the microwave has 2000 watts or 2 kilowatts is the power which is injected in the port. And then port 2 is the other port where the signal comes out. Okay. Now we specify a convection boundary condition to all the outer faces of the copper, and then we do a simulation. And I've already done the simulation, and we can jump right into the results. So a couple of things that interest us. First is the electric field. Let us look at a section plot of the electric field only inside the dielectric. So the program allows you to do that. You can actually take a look at the electric field. And you notice here that it's about 5.39 e to the 4 volt per meter, and it's much less than the breakdown voltage of the dielectric. So that's something that we don't need to worry about as of now. And you can also look at the electric field as a vector plot inside your entire structure, and this tells you how the electric field is distributed. Okay. And then we are more interested now in the thermal simulation, so we're going to take a look at how the temperature distribution is, and this is the temperature distribution inside my model. You can see here how different parts of your model gets heated. Specifically what we are interested in is the dielectric and how the thermal properties, how the temperature is distributed inside the dielectric. So we can take a look at it in a familiar notation, which is Fahrenheit. Notice here that the dielectric really at 2000 watts is not really getting heated much. It's about 84 Fahrenheit, and something that is certainly acceptable for the functioning of this device. So thus HFWorks really helps us to understand not just how your RF and microwave devices perform, but also thermally how do they perform in case of peak power, as well as the continuous operating power conditions. With this, we will revert back to our application slide here, the PowerPoint, and that concludes the demonstration part of this webinar. So just as a recap of what we saw today is really the ability of HFWorks to handle two different kinds of power conditions that engineers are interested in. One is the peak power, and as we noticed here that HFWorks is capable of plotting the electric field plot and identifying areas inside your model where there could be a dielectric breakdown. The next one is the continuous power operation, and this is really where the thermal part comes into play. It helps you to identify hotspots and identify in your model which are the areas that can get heated. Isoplots help you to identify zones which get heated above a certain value, and so on. Again, as a recap to people who are watching this webinar, if you are interested in availing a 1-month free trial of HFWorks, please send an email to sales@emworks.com with this following subject: HFWorks 1-month free trial. You will be getting 100% customer support during your trial. We want you to succeed. And after the trial option, if you decide to buy, you will also be able to purchase HFWorks at a discounted price. For details regarding this, please email our sales department, and you will I can assure you that you will get an immediate response answering all of your questions. Now with that, I thank you all, and on behalf of EMWorks, I thank you for watching this presentation, and look forward to seeing you in another presentation. Thank you very much.